In example 7, we're looking at retrieving the max value, but in this case, we're using a subquery as part of it. Down on the note portion of the page, and you can consult with the eKit and have a look at this page. But down here we have additional information on some of these, and they're very good to have a look at them. You should be reading all the note pages as you review the material later. Okay, and we give you additional information in here. I cover the salient points. If we have to cover all of them, it takes a little longer, but some of these are interesting to have a look at, and the key points of the slide were actually in the notes. So this query was intended to retrieve the latest state when a product was sold by a customer and then return the sales detail for that date. However, the query does not return the correct results. In other words, it was incorrectly written. And the main reason why, it was written as a non-correlated subquery. The inner query gets executed once and then the outer query. So it actually doesn't calculate it individual for each subdates. So to correct this deficiency in the SQL, they need to really restate it as a correlated subquery. Now we've got the outer query and we've put an alias on the sales on the outer query, and that is referred as part of the query in the inner query. So this makes it a correlated subquery. Okay. The downside of needing to use a correlated subquery is the inner query needs to be executed for each row in the outer query. That makes it more expensive to process. If it could have actually been stated as a non-correlated, then we would execute the inner row once and the outer, then just do the outer query. So it would actually be a cheaper query to execute. But this will return the correct results, which were what we want to do. Okay. Now, because we have to execute the inner query many times, the question becomes, how does it perform? So they had a look at the output from tkprof, and it actually didn't perform too badly overall. In terms of the number of blocks we had to look at, we visited 8 blocks in memory to retrieve 1 row. Okay. Is there a way to reduce the cost? Perhaps we could use an index to reduce the cost of doing the fetch operation. So they're looking at tuning the query. So if the time ID column is part of your index, in this case it is, it's part of the primary key for this particular table, okay, on the sales table, okay. So then we can re-execute the query, and this time they're just looking at a portion of the query to see if they can get it to use the index for the portion they're interested in. And when they execute it this time, okay, they actually was able to use the index. We reduced the cost, and it's really the logical reads off of this, because we're generally flushing the database buffer cache between reads. We expect to force it to reread, okay, but it's the reduction in number of logical blocks we're really looking for, and it was able to reduce it in half. That actually gets a corresponding reduction in the time to execute it in terms of the CPU and elapsed time. Went down to less than we could measure it to what we could actually measure it, okay, down to our resolution. So the next query is another example of a correlated subquery. Okay, so this time we're going to go in and have a look at a calculation that calculates an average salary for a department that a particular employee work in, because we need the average salary for the employee's salary. We have to do it as a correlated subquery, retrieve a row from the outer query, and apply it in the inner query to calculate the average salary. And when we looked at the execution plan for this, it was able to go in and access the table and ended up doing a full table scan on the employees table. We're just reading through the table on the outer query to get candidate rows to execute the subquery. In the inner query, it used a range scan on the department ID. It found an index that allowed it to do the access. Are there other options to tuning this query? They are. And for this one, they actually have the output, so I was just showing what was in the bottom. So let's go have a look at their output the way we did in the previous example. So I go back and forth between this. So this should have been example 1, 8. And we have 2 examples of the query, 2 versions of the query they try. First one we'll take a look at. Okay. We're going in and doing this correlated subquery after we take off all the tracing information. And it has an order by clause on the outer to get it by the department. We'll have a look at the full execution plan so we can get the performance information about it. And in this execution plan, they had to touch 13 pages, 13 blocks in memory for the database to retrieve 38, okay, rows out of the table. And this was the one they were doing the range scan on it, okay. Because we have an order by clause, okay, and we've got to group it up to do the order by calculation, they have a sort group statement. We're using an average function. But they have a note in here, it was a sort group by to do the grouping, but they didn't have to sort. The index was able to provide the data by using the range scan in the order we needed, so we avoided the sort to do the group by to apply the average salary, because the index just retrieved the one group for that employee that we wanted. But we still had to do the sort to get the order by at the end. We had an order by clause. We still needed to do the sort for that. So there's a second version of the query that we have a look at in 8.2. Okay, this time we're going to go in and calculate the average salary. And we've changed the query a bit. We've added a where filter to it. And we're also want to have a look at an additional condition. So we want to know when a particular employee's salary is greater than the average for his department. Okay, is he on the upper end of the department's salary, or in the middle, or towards the lower end? Okay. When we have a look at this query, which is a slightly different variation on it, we'll have a look to see how they actually did this one. Okay, so this time we visited 15 blocks to return 38 rows from the query. And this time we did a hash join, okay, a hash group by, and we used a inline view. We had restated the query. Instead of being a correlated subquery, as it was earlier, we took the correlated subquery and we rewrote it as an inline view. So the question becomes, so it was able to pick a different access path and ended up hash joining the 2 tables, did a full table scan of one table, did a hash group by function to group it up, and then was doing a full table scan of the other table. And it used 2 copies of the employees table. So overall, was this a win or a loss by changing the way we actually wrote the query? So we'll just look at the outputs, 15 to get 38 rows. In the previous example, we touched 3 to return 38 rows. Used in our original would included the sort. And in that case, this one looks like it has a very slight advantage in terms of reducing. Sometimes we try some options, do it as an inline query, and sometimes doing it as a correlated nested subquery. Gives the optimizer two ways of looking at the data. Came up to two paths. Sometimes one is better than the other. This case, the first one was a little better, and that's just typical. To really proof of the pudding is to test. There wasn't a lot of difference in the time. No, there was some. So even on time-wise, this was a win. So I would go generally with the first one. Now the problem with doing the sorting here, the second version avoided the sort. So if we were looking at larger volumes of data that we had to sort, with a few rows, we can probably sort them in memory, and then sort becomes an efficient operation. If we have to sort a lot of rows, then maybe it spills over to disk and it's not quite as efficient. So I would be careful with this, making sure we're looking at reasonable volumes of data, because with different data volumes, the story may change. Sorts don't tend to scale up very well, so just be a little careful with that. Okay, so we're continuing on with the material. So down in the next example, okay, we had a look at our two variations of the correlated subquery. The next up is having a look at a union and a union all, okay. If we can guarantee, okay, when it processes a union, not a union all, it essentially does a union, which will return duplicates, and then it does a sort unique to remove the duplicates as part of the processing. If I could guarantee there were no duplicates between the two sides of the query that I'm union, or end sides of it, because you can actually do more than two in a union statement, okay? If we can actually guarantee there are no duplicates, then a union all would be a more efficient. Or if we can find a way to avoid the sort unique, because we can find an index that would return the data, and that's usually a little harder to do generally, okay? So we have a couple options to look at this one, okay? So we have a little example in the demo to have a look at this, so we'll take a quick look at this. And when we come back, we'll be looking at that one, so I'm just skipping ahead a little bit. Just to clean things up, we'll get rid of those examples. Go to 9.1, open it, display it, okay. And this was demo 9.1, where they're having a look at a few different options to have a look at unions. So we're just getting an idea of the data. They're doing the count of stars that where the customer is, their first name is Max, okay, or the last name is Collins. And when they execute this, this is just a little comment, they actually expect to return about 127 rows overall, okay. A second way of expressing, those are just little indications they put in so we can discuss it. A second way of expressing this OR condition is as a union. We just do the two individual queries, okay, so we do the select from the customers, where a customer is Max, union it with the second select, where the customer's last name is Colvin, and then we just union together, and then we're just looking for the count of number of rows we get back total. And when we do that, it gets the exact same answer. It gets the same rows, the same number. They're just two different ways of doing it. Now, the advantage of doing it this way, if we do it this way with an OR condition, if we have appropriate indexes on the column first name and the column last name, once we OR them together, it won't use an index. It will do a full table scan. In this case, we're not ORing them together, we're just treating them as two independent query blocks and then joining the results together logically with the union operation. Then it opens up the opportunity to use the indexes for these two, what look like logically standalone queries, where if we OR them together as a predicate, it will throw its hands in the air, okay, to actually do it. Now, in this case, they wanted to demonstrate that you need to be careful that it returns the correct results, okay? If you do the union all in this case, there are some duplicate rows being returned, okay? So we can't use the union all to replace either of the top two unless the application is really expecting to handle duplicate rows. If it's expecting non-duplicate rows, that's a problem. And then depending on how many duplicates we have, what we potentially can save in the sort on the server, and this is a fairly modest sort, we may end up, if there was a lot of duplicates, we may end up losing on the network. We got extra data to transmit through the network. So sometimes you got to look at the query and then you got to look at the big picture. How much data are we reducing it by sorting it? Maybe we can get an index, a little harder sometimes, maybe we can avoid the sort. Okay, so we have a look at a couple of these queries just to compare and contrast them based on what we just talked about. So open the output for them and we have them. The first one is just doing it as the OR, okay? And generally it can't OR balanced trees together, which are our basic indexes we're using on this. Interesting enough, starting in 9.2, the server can actually make a decision to convert a balanced tree to a bitmap index. You treat it as a bitmap index where it can actually OR bitmap indexes. Bitmaps are made up of bits and bytes. Computers are made of bits and bytes. There are very efficient algorithms to AND and OR bitmaps together on computers. Some of them on some operating system, they even have hardware assists to actually facilitate that. And it will use this option if it perceives that the cost of converting it to a bitmap index and using it internally as a bitmap indexes and then converting back to the row IDs is less than doing a full table scan. So the bigger the tables are, as long as the indexes are reasonably compact, the more efficient it looks. And it chose this one because it turned out to give it an overall lower cost than actually doing it as a full table scan. It would have to look at a lot less blocks. And the cost of the conversion was low enough to make it a desirable access path. Looking at the next one, we'll just roll it up to the top of the screen to make it a little easier to view. Now we're doing it as a union, okay? When it did this, it had to access the two. It essentially used indexes to access them, okay? But it couldn't use the indexes to retrieve them in the right order, so it ended up doing a sort unique, okay, and then an aggregate to do the account, okay? And we treated, there was an outer query and an inner query. We treated the inner query as a view, essentially. This one, it actually did. It was a little more expensive than the previous case. And I would suspect it's probably a little cheaper than doing it if we did it the previous version as a full table scan. That's why it picked the bitmap conversion. But if the data is larger, the data is, we have to sort, the more expensive this sort unique becomes as part of the operation. This one, we did a sort aggregate because we did a count, which is a group function, but it actually doesn't do the sort. It has one group and it doesn't have to do the sort to get the one count. Even though we document it as a sort operation, it doesn't really sort. The final variation was seeing how it performed when we didn't do the sort by doing the union all. That allows it to drop the sort to make the rows unique. And now it's back into the same number of blocks that we had in the very first case. We actually touched 4 blocks, okay, and retrieved it. And this time it did the union all, it did 2 range scans, but because we said we're happy with duplicates, it didn't have to sort to remove it, so it reduced the cost down to 4 blocks from the 23 we saw previously, which was on the same order as this one, except it didn't have to do any conversion of the indexes. So generally that would say CPU cycle, especially when you scale up with larger amounts of data. But can the application tolerate the duplicate values? If there's enough duplicate, don't forget, you could take a hit on transmitting the data from the database server to the client, whether the client be a middle tier or an end client application. And after a point, which you gain in processing a database, you may lose on the network traffic. So you got to sometimes look at the big picture as we're having a look at these. So the next one is avoiding use of a halving clause. This is just an example of a mistake in writing SQL, using the wrong clause in the wrong place. So once again, it explicitly says something about the way you write the SQL. A large number of the examples in here are around how you write the SQL and how it influences the optimizer's ability to make decisions and what decisions it actually makes in the environment. So in this case, we're looking at the customers table. It has a customer city index, one on the customer's city that his facility is in, okay, that's built on the customer city, and we're doing a couple of queries, okay. We're selecting from the customers table, the city and the average customer credit limit within that city for customers that live in a particular city. So we're doing the from clause. To get the average calculated, we need to do the group by, okay, and then we use the halving clause for the customer city the constraint on the customer city. But the halving clause is intended to process any of the group by functions where we want to pick a limit on something that's calculated as a group by. If we wanted to limit the average customer credit limit to be above a certain amount, then the only place we can put it is in the halving clause. And that would be a correct use of the halving clause. The statement with the group by statement is processed in 3 steps. The first thing we do is we do the select, including the from clause and the where predicate. If we had a where predicate after the customer, it would apply the where predicate. It's accessing the data at this time. Any predicates in the where clause is actually can use an index to filter the data. Then we've accessed the data, we group it by the customer city, and then we apply the halving clause to reduce things. And the intent is to reduce things like the average customer credit limit, put a constraint on that. And we have to wait before we can do that after we've done the group by, calculated the average, and apply the halving constraint. So because the customer city has an index and we put it in the halving clause that is processed after accessing the data, unfortunately we can't use the index. The correct way to state this, since we don't have any calculations on the average customer credit limit, but we can limit it by the customer city, is to put the customer city predicate in the where clause. Now we'll use this upper portion to access the data. We can apply the index to give us a good access path to filter it, group the results we get back, calculate the average salary, and then if we needed to limit it, put the halving clause. Since we didn't need to limit it, because we weren't limited it by the average salary, we just left it off. So don't use the halving clause unless you're included something you're limiting by a calculation from a group function. That's the main gist of this example.